Hello, everybody. Wow, you can really hear me. That's loud. I'm going to have to tone it down. I have a teenage daughter, so I'm used to speaking very loudly, so she actually recognizes my existence. I'm hoping I don't. It is the last session of the day, so maybe I should be talking loud here. All right, we're going to get started. These guys have me on a very tight schedule, and I also have a train to catch, so I really do. So we're going to end right at 6:05. So let's get started. All right, the Twitter pitch. I love this. When we were raising money, I remember in 2005 for my first startup, they were saying, you got to have the Twitter pitch, which is a 140-word description of what your startup idea is. So the Twitter pitch here is that there's this whole class of problems that are valuable problems that you can solve if you can do good similarity. And by good similarity, it's fast, accurate, scalable. Usually when you hear someone say those three things, they're going to say pick any two. Right? Like it can be consistent, it can be reliable, it can be whatever, scalable, pick any two. In this case, we're going to talk about ways where sometimes you can get all three. So I've been using Hadoop since actually before it was Hadoop, back when it was part of the Nudge project in 2005, 2006. So because of that, I've made a lot of mistakes over the years, and you supposedly learn more from your mistakes than your successes. So I'm hoping to share some of what I've learned in applying these techniques to clients. So I have a consulting company called Scale Unlimited. We do training, we do consulting. And what I'm going to be talking about here are some of the actual projects we did that involve similarity. So what are some examples of similarity problems? So one of them is clustering. For example, we have a client. They extract information about display advertising. So millions of pages every day get crawled. You find the ads that are showing up on those pages. And they wanted to cluster advertisers. What are similar advertisers? So clustering is all about figuring out whether two things are close to each other, are similar to each other. Essentially, you're calculating a distance between them. And things that are more similar, that are closer together in distance, get clustered together. So clustering is an example of something that relies on being able to calculate similarity. Deduplication. So we had a client that had two sets of data of points of interest. So places in the US. And these had a lot of overlap, but they were different data sources. So they didn't exactly match up. Sometimes it's because one data set is a little bit newer or older than the other data set. Sometimes it's because of errors in the data. How do you do deduplication? It's another example of fuzzy matching, of similarity. I'm not going to talk too much about those first two because of time constraints. The next two are what we're going to go into in more depth. So one of them is recommendations. A key part of recommendations, and we'll talk about this more when we get to that, is calculating similarity between users. You want to find similar users in order to make good recommendations based on what they've done. So again, it's a similarity problem. And then the last thing is entity resolution. Let's say you have information about hundreds of millions of people and places, people and companies in the US. If I give you some information about a person, can you quickly find all the people that this might be? And this has to do with things like opening new bank accounts and essentially fraud detection. All right, so I've got to do a brief overview of similarity in general. Exact matching is easy. Right? I mean, the open source space is lousy with key value stores, where if I have a unique key, I can very quickly find the thing that it represents. So if I'm doing exact matching, I can do something like take all the data in this thing that I've got, hash it, and I use the hash as the key. I could throw that into Cassandra, HBase, whatever, and if I've got a key, I go and I look for it. If it's there, I'm good. I've got an exact match. If it's not there, I don't have it. Now, of course, when you talk about scalability and getting to the billions of things, any problem becomes hard. Right? But compared to similarity, to fuzzy matching, it's way easier. Right? Fuzzy matching relies on, I've got these two things that aren't exactly the same. So I can't just get a hash of it and use that to do a lookup. So in similarity, I'm comparing features. So what are these features? Here's an example. Let's say I've got two text articles. Right? And the features here are basically words. It's a bag of words. So are these two articles the same? Who would say these two articles are essentially the same? Close enough that you'd say, yes, I'll call them the same. Nobody. What's interesting is these are two articles that are different versions of the same page from Wikipedia about Bosnia and Herzegovina. Right? This is just two different versions, one from 2 years before the other. So essentially, this represents just a mutation of the page through editing. What's interesting here is this was the initial set, and then I could edit some words, and I could make it in some ways easier, in some ways harder, to decide whether two things are similar or not. As soon as the problem becomes one where a person looks at it and says, I don't know, maybe, like if you get 10 people and 5 would say yes, 5 would say no, then that becomes an impossible problem for a computer to solve. In this case right here, the challenge is there's conceptual similarity versus sort of data or editing similarity. We're not going to try and solve the conceptual similarity problem. That's like if you want to get your PhD at Stanford, go and solve the conceptual similarity problem. Here what we're talking about is more like mutations of things. Is this thing with a sufficient amount of like editing equal to this other thing? Not two independent versions were created, and do they actually represent semantically the same thing? Now we've got other kinds of similarity issues around records. Remember when I talked about like identifying people in a fuzzy fashion? So if I have these two records here, right, fields and records, those are the features, you could look at this and say, yes, these are the same person. Right? Everybody knows like Bob and Robert, that's just a synonym. And in one case I've got a zip plus 4, in the other case I just got a zip code. That's an insignificant difference. Right? I can make it a harder problem. I can say, here's two versions of this where there's been more sort of perturbation on the data. So who would consider these two records the same person? Who would think, if I asked you, like, are these the same person, who would say yes? Who would say no? A bunch of people would say no. What's interesting is this is a kind of common example of two records that actually are the same. And it's due to all kinds of problems that you get with data sets. There's the obvious one of Bob and Robert, and there's a missing middle initial in one. In one case, they left out the apartment number, right? They have it in the other one. There's a typo here where they added a 3 in there in front of the street number. These guys, this is not a significant difference that you didn't have the zip code. That wouldn't be enough to say it's not the same. So actually, you'd want to consider these two things to be the same. Now we get to the third example, which is around recommendations. Let's say I've got two users on Amazon, and I've got their shopping carts. I've got what they're buying. User 1 bought the things in the first column. User 2 bought the things in the second column. Are these two users similar? Like, would you say they were the same kind of user? In this case, it's pretty easy. I look at it and say, well, the difference between the first two are capacity. One's 8 gigs, one's 16 gigs. And the second is both critter cams. And the third one is both different versions of an ice axe. Not so hard. But, of course, I can make it harder. So in this case, what we've got in the first row, these two things are kind of related, like a memory stick that you put in a camera, but there's no similarity between the descriptions, really, of those products. Right? The second thing here, they both kind of look like they're camo colored or something, so maybe they're related. And the third thing, if you, as a person, you look at it and say, great, they're into mountaineering. Ice axe and crampons are similar, but there's no similarity in their descriptions. So now you start talking about, well, maybe I could use product categories as a way of saying these things have some similarity, right, as the feature. There's actually a much better way to deal with this, which we'll talk about in the next section. All right, and then the last thing is, how do you measure similarity? So let's say I got these set of features, right, of two things, and I'm comparing them. How do I actually come up with a measure of similarity? So really what you want, because we're talking about computers here, is you want a number. It goes from 0 if things are completely different to 1 if they're exactly the same. That's what you like. You want to calculate some number. So how do you do that? Well, there's a whole bunch of techniques. There's two simple ones I'll talk about here, Jaccard Coefficient. Right? What this does is basically says, let's come up with the unique set of things, and then let's say how much overlap there is. So obviously, if the amount of overlap is complete, like everything in the first set is in the second set, and there's nothing that's not in either set, then that's a 1. Right? If you take the number of things that are in the intersection divided by the number of things that are in the union, which is this part of the equation over here, that gives you a number between 0 and 1, where 0 means no overlap at all, the two circles don't intersect, and 1.0 means the two circles are exactly the same. So that fits our model for what we want for similarity. Now, there's another common technique called cosine similarity. It's just what's used inside of Lucene, a lot of search engines. Essentially, you create a feature vector. So let's say I only care about 3 words, cat, dog, and goldfish. And I create a feature vector, which is going to have 3 numbers in it. The first number is going to be the frequency of the word cat. What percentage of the words in the document are cat? The second one is what percentage of the words in the document is dog? And the third is what percentage of the words in the document is goldfish. So that gives me a three-dimensional vector. Right, you can see we got this vector here that's going from the origin up to P. Now, if I have another document and I do that exact same thing with it, I'll get another vector in there. And if I take the cosine of the angle between them, I'm going to get a number between 0 and 1. Now, because these numbers are all positive, right, each of the values that go into the vector are all going to be greater than 0. Everything's in this one portion of the quadrant. So the maximum angle between anything is 90 degrees, which is why cosine of 90 degrees is 0. So that's why they're completely different at that point. So obviously, when you have documents that have thousands of unique words, what you get is a feature vector that's got thousands of dimensions. But with linear algebra, it's easy to calculate the angle, the dot product between the two vectors. Okay? So this is cosine similarity. All right, now why is scalability hard? We kind of talked about issues, the challenge of similarity, but why is scalability hard? Well, think about this, the example I talked about where I'm deduping points of interest data. So let's say I got 8.5 million points of interest in the US. And what I want to do is I want to say which of these are the same. So if I'm doing the comparison, and I assume that this is symmetrical, so if A is got a 0.7 similarity with B, then B has a 0.7 similarity with A, then the number of comparisons is roughly n squared divided by 2. Right? So what that means is for those 8.5 million entities, that's 36 trillion comparisons, which even with Hadoop, that's not something you want to do. Right? If it's billions, if you can count your billions, you can do it with Hadoop. If it's into trillions, it's like, maybe not so much. So one of the things here is often you can do a trick where you have the magic field. So in this case, the way we knocked the problem down is we said, if two things don't have the same zip code, we're going to treat that as a source of truth. And if they don't have the same zip code, they're not ever going to be similar. They're not going to be the same thing. And so just doing that kind of reduction, because it's an n-squared problem, if you can create smaller groups, the size of the problem drops dramatically. And it actually dropped down to about 4 billion comparisons, just grouping by zip, and then only comparing the things in the group that had the same zip code, suddenly becomes a tractable problem with Hadoop. But often you don't have that magic field. So let's get to the first example. So one of the things my company did is we created the Solr training materials for DataStax. So DataStax has got DataStax Enterprise Edition, which is a combination of Cassandra and Solr. And one of the modules they wanted was something to do with machine learning. So we created a recommender using essentially Cassandra and Solr. And the recommender we created recommends web pages on the DataStax site. So we're going to talk about what that means. So the issue is, how do you recommend web pages when somebody's browsing your website? The normal way that you recommend web pages is you put links to those pages on the page. Right? The first problem with that approach is it's incredibly tedious. Like, if I was responsible for doing the linking on a large website, I would probably have to shoot myself. Like, I can't think of anything more tedious. And obviously, it doesn't really scale well. Like, if you've got lots and lots of pages, how do you do it? And the third thing is, you run out of real estate. Like, everybody wants to be in the top left corner of a web page, right? Every group, right? Everybody wants to own that corner. So that quickly gets a little busy. It's a busy neighborhood. So is there a solution here that uses recommendations? Well, what we're talking about here is exploiting other users' activities. And this is often known as shopping cart analysis. Users who bought X also bought Y. Like, anybody who's bought anything at Amazon and checked out, they'll see that. The really cool thing about user activity is that it's so much, there's two things about it. One is it's so much better than user ratings for recommending things. Because with user ratings, there are typically two kinds of ratings you get. One is somebody's incredibly pissed at you, at the product, and so they want to do that rating that's really going to show you like how bad your product is. And the second one is super positive ratings by people who are paid on Mechanical Turk to write bogus product reviews. Like, those are two of the most common signals you'll get when you're using ratings. So that's noisy. Versus what people bought, that's real intent. That's like the gold. So we can actually use user activity here, where we can say, for example, people who bought this CritterCam also typically bought these things. And now notice here, it's a security box, right, for a camera, for a CritterCam that watches for motion and automatically takes pictures. That was the thing that was in that second example of, are these two users the same? And I said, well, they're both camo colored, so maybe they're similar. Well, in this case, we're getting sort of similarity because they're often bought together. It has nothing to do with like their description or their product codes or any manual classification. It's just user activity. All right, so how do we actually take advantage of this data? So what you do is you collect the web logs. And the web logs are classic web logs that have an IP address, they've got a time, and they've got a page. Now, if you run these through a Hadoop workflow to clean it up, what you can do is you can create sessions where for the same IP address, without a significant gap between activity, that's a session. That's a user browsing around on the website. That's like a shopping cart. Okay? One of the reasons you have to run it through a Hadoop workflow is all data is noisy. In fact, one of my rules of thumb is the first time I try and do anything with machine learning, if the results are really great, somebody's messing with me. Like the results should always suck the first time. If they don't, there's a problem. Like I'm not understanding the problem properly, or somebody's giving me bad data, like data that's too clean, because you always have to clean up your data. And it's an iterative process where you try something, and the results are bad, and you figure out why. And often it's because your data is bad, and you have to do more data cleansing. And anybody who deals with data science tells you that's what you got to do. You've got to look at your data and clean it up. So we had to do things like get rid of fetches of image pages and get rid of all the bots, including get rid of all the bots that are pretending not to be bots. Like get rid of all of the web accesses from the same IP address where there were like 5,000 of them in an hour. Right? Nobody's clicked on 5,000 pages in an hour. So all this data cleansing to come up with clean data we can use as our features, as our signals. So once we've done that and we've got these sessions, right, now we've got a similarity problem. Because if we can find sessions in the past that are similar to the current user's sessions, that gives us our relationship that we want. Because then what we can do is we can get these similar sessions and find what pages they've looked at that the current users hasn't yet looked at. And those become interesting recommendations. Right? So how do we actually do that? Well, we create a Lucene index using Solr, which has basically got one document for each session. And the document consists of two fields. The first field is just the unique key field, which could be anything. It's a session ID. It could be the IP address and the time of the first request, right? It's just some unique field. And the second field just has all the pages that were viewed during that session, the paths to those pages. Right? That's our data. Then what we do is we take the paths from the current user session, and you do a search in the index in that field that's got all those paths. And it comes up with similar sessions. Why does it come up with similar sessions? Well, search is essentially similarity. What search is doing is it's taking your query and it's essentially creating a term vector, a feature vector out of your query. And it's comparing it to the feature vectors for documents in the index and calculating that cosine similarity angle between them and ranking them by how similar they are. Like in a simplified version, that's what it's doing. So what we're doing here when we do that search is we're finding sessions that are similar to the current target user sessions based on what pages they looked at versus what pages the user looked at, the target user. Right? So once we've got this candidate set of sessions, like let's call it 50 pages, right? 50 sessions. We find 50 similar sessions. And for each one of those sessions, now we go and we do our own similarity calculation using the Jaccard coefficient between that session and our target session. Any page in those sessions that the current user hasn't seen yet, we collect and we add the similarity score to it. And at the end, the pages with the highest similarity score wind up the ones we recommend. So why are we summing similarity scores for pages? Well, the fundamental concept here is pages from sessions that are more similar to the target user are more interesting. Right? Like let's say I have some user who, let's say it's a shopping cart. I got one user who's bought, 5 things, and my target user's bought 4 things, and 4 of the target users' sessions, things in their shopping cart are in the other shopping cart. That shopping cart is incredibly similar to the target cart. So the one extra thing in there, that's gold. Like that's a really useful thing to recommend. So in this case right here, let's say we got 2 sessions that we found in our search. This one has an overlap of 2 out of 5, so its Jaccard coefficient is 0.4. So D and E, I'm going to give each of those 2 pages, let's say, 0.4. And then I get to the second session. The overlap's only 1. So it's 1 out of these 5, so the Jaccard coefficient is 0.2. So I'm going to add 0.2 to each of these. So the end result is I wind up with 3 pages that I could recommend. This one's got a score of 0.6, this one's 0.4, this one's 0.2. Right? D is most interesting because it's in both of these sessions. Okay? So it's a simple technique. What's interesting about this technique is it's real-time recommendations. Like as web pages are being viewed, and basically I'm processing these logs that are coming in, I could be continuously updating my Solr index. And so for certain recommendation cases where you need it to be immediately reactive to what's going on, it works really well versus traditional recommendation systems where you take all this data and you run it through a big Hadoop batch job, and you come up with sort of the data that you then use for your recommendations, right, which can't be that reactive. It can't be that real time. So there are some problems with this approach, and one of them is the classic everybody loves puppies problem, I think as Ted Dunning described it. The problem is, like, almost every session's got that top page, the www.datastacks.com page in it, which means if I'm a user browsing and I haven't looked at that page yet, it's always going to recommend that page, because that page is going to show up in every other session, that's similar to me. But that top-level page, that's not a very good recommendation. Yeah, OK, great, the top-level page. I could care less about it. It doesn't have any real meaning in the context of my session. So it stinks as a recommendation, is the problem. So is there a way to deal with this? There is. So we're already talking about using Hadoop for pre-processing the data to create features. But there's another thing that's in the Mahout open source project, which is a project about scalable machine learning, called the row similarity job. And row similarity job is really interesting. What it does is it takes in data saying, I have rows that are users, and in each row I've got the items the user is interested in, whether they bought them, they viewed the page, whatever. It generates a matrix out of this, an item-item matrix that says what's the sort of significance of the co-occurrence of items for users. What that means is it comes up with scores for each item-item pair that says how surprising is it? How unlikely is it that these two items occurred together for, say, several users as often as they did? So that kind of gets rid of the everybody loves puppies problems, because the top-level data stacks page is in every single row, and so it doesn't have what's called a high log likelihood ratio score. And those are the numbers that go into this item-item co-occurrence matrix. Right? So these common items get very low weights, and what you get left with is this item-item matrix. In this case, it's an example of page to page. Like page 2 has a very high score, which means a very high significance of co-occurrence with page 1. And page 3 is a lot lower. So what I can do when I have this matrix is I can drop the least interesting scores. I can get rid of everybody loves puppies. And now I've got this matrix that I can turn into an index. What I can do is I can create one document for each page, and the values, the things that I put in here are the pages that have high enough log likelihood ratio scores. So now I've got an index where it's page 1, page 2, page 3, and over here I've got highly correlated pages. So now when I have my target user and I've got the pages that they're looking for, I can just do a search in this field in the index, and the top hit is going to be the one that I want to recommend. And the number 2 hit's going to be the second one I want to recommend. And that works really well. Right, so it's a combination of using Hadoop to generate this co-occurrence matrix, and then turning that into something that I can quickly search on using Solr. And actually, this guy, Pat Farrell's got an open source project that does some of the bookkeeping that you need for this, because one of the problems with row similarity is that that job assumes that all the data you give it is integers. So you first have to build a dictionary that maps from, like, here's an item name or a page to a number. You do the calculation, and then you have to convert it back. And he's got an open source project that does that for you. All right, so now we come to the second one. So that was the one about recommendations. Right, now we come to the one about sort of entity matching and fraud detection. So what is early warning? Early warning services, it's one of these companies that nobody knows about, but it's like really significant. So the issue here is that banks have to deal with the problem of fraud that occurs between banks. So as an easy example, I open an account at 2 different banks. I take the same check. I deposit it in both accounts, and really quickly I pull the money out of one of the accounts, or both the accounts. Right, so I've doubled my money. Well, how do you detect that? The only way to detect that is if you shared information about all those accounts. Okay, there's no way in hell like Wells Fargo is going to send its customer list to Bank of America, right? These are competitors. Right? So what they did is they created a joint venture. The top 5 US banks created a joint venture, and eventually now it's like 800 financial institutions send their data to this one company every day, right? Huge amounts of data. So they have details on pretty much every US bank account. So now the question is, when somebody signs up for an account, like if I go to some bank and I say, hey, I'd like to open a new account, they collect some information from me. They want to know, should I open an account for this person, or is this person going to immediately start bouncing checks or commit fraud? Right? What do you do? Like they want to get back a risk score for opening the account. So let's say you've got information on hundreds of millions of entities. It's people, it's companies, right? You got lots and lots of information that includes names, addresses, sometimes things like social security numbers, phone numbers, driver's license numbers, et cetera. A whole bunch of data. Why is this a similarity problem? It's a similarity problem because the data is noisy. The data in the index has issues, like when somebody entered the account data for a person, they did a typo, right? They misspelled the person's name. They even have typos in social security numbers, right? It happens. It's crazy, but it happens. And then the other problem is, well, and then you have the problem with the request coming in. The information that somebody enters when they're opening the account, they're doing the same thing. They're typing away, and they'll have typos in that. And the third thing is, it's hard to believe, but people lie. Like people who are especially trying to open a fake account, they lie. And they give you munged data. They'll swap the street name and their last name. Right? What they're trying to do is come up with an alias that they can remember. Right? They'll do things like that. And so the combination of these means you got a fuzzy like similarity problem, a fuzzy matching problem. All right, so how does search help here? Well, what happens is you can use Hadoop workflows to take all that raw data that's coming from all these banks and building an index out of it. Once you've got this index with all these fields for like name and address and phone number, I can do a query against it with the data that I'm getting in from the inquiry. And I can get candidates. I can get like, here's the top 100 entities that look like they have some similarity with that query. And that happens like really fast. Like even for hundreds of millions of things, it's like less than a second, typically 200 milliseconds. And then once I've got this candidate list, then I can do the more specific comparison, which is often very domain specific, right? So Solr gives me general similarity. The matching that happens once I get the candidates back is really for each use case. What's the importance of a typo in the social security number versus a typo in the last name or a change in a letter in the last name, right? That's all very domain-specific scoring. But the end result is I've got a list of entities with scores. You can take a cutoff threshold, which always is kind of painful, but you can just say whack, get your weed whacker out and say everything with a score above this is a match and everything with a score below it isn't. Once you've got those list of matched entities, you can go look up their account status, how many bounced checks do they have, are they on the fraud watch alert, and you can come up with a risk score. How much would you want to or not want to open an account for this person? Okay. So this data pipeline, I mentioned, you take Hadoop and you pull all this data in to turn it into the index. Well, what's happening there? One of the things that you have to do is you got to clean up the data as much as possible, which means normalization, like lowercasing everything, getting rid of spaces, maybe doing some simple like number reformatting for phone numbers to get it in a standard form. Zip+4 is an example. Sometimes you have a Zip+4 zip code. Sometimes you just have the zip code. Sometimes you got no zip code. So what you want to try and do is create as clean as possible data in this phase and also then leverage what Solr does naturally. Like Solr does synonym expansion. It's really easy to set up synonym expansion in Solr where it's like Bob, Robert, Robbie, et cetera, are all essentially the same. And Solr does a really good job of that. We take the resulting data from Hadoop that's been normalized and we throw it into Cassandra. Right? Cassandra is a key value store, gets thrown into Cassandra. As it goes into Cassandra, because it's DataStax Enterprise, is indexing it automatically with Solr. So the end result is we've got a Solr index that we can run those queries against. Now the other thing that's interesting that you can leverage with Solr is on a per field basis, you can do very different kinds of analysis. How you split up text, how you create synonyms, how you normalize, et cetera. So for example, on the name field, we've got all these name synonyms. Right? That's something that happens there. you split up the field into multiple pieces, like the address field. If you just split on spaces, then you get like, here's the street number, here's the street name, here's the street abbreviation, which means if they have an error in one piece, like the street number like we saw, you'd still match partially that field with the other values that are in there, the street name, et cetera. So it's not like you get a complete miss if you split things up into multiple pieces. Right? And at query time, you actually weight the queries. So obviously, like a match on a social security number, that matters a lot more than matching a first name. Right? So you can actually tell Solr, I'm querying against the social security number field, and it has a higher weight. It has a weight of 100 compared to querying against the zip code, which has a weight of 4 for if it matches. Okay? So that helps improve the ordering of the candidates that come back without doing any kind of crazy helicopter stunts, like messing with the similarity class that Solr uses for scoring. All right. So far, what we've been talking about is kind of a mix of Hadoop as a data processing pipeline and then using Solr as real-time queries. But what happens if you have to do batch similarity? Right? So you have a whole bunch of things that you got to sort of essentially dedupe. So in this case right here, search isn't great. Like if you had to do 100 million queries against the Solr index to deal with like resolving entities, that would be a bad idea. Don't do that. All right, don't do that, because that would take a really long time. So there are techniques, though, to do similarity in Hadoop. And we're going to talk about two of them. One's called SimHash, and one's called parallel set similarity joins. So SimHash. SimHash works well for documents that have a whole bunch of words in them. If you have a whole bunch of words in them, then what you can do is hash each word, come up with a hash code for each word. If you then sort those hash codes and you pick the minimum value, the probability that the hash code, the minimum hash code is the same between two documents is the same as the Jaccard coefficient between those two documents. That's the magic part. So it's basically like if I have two documents and let's say 90% of the words are the same in those two documents, if I hash each of those words and I take the minimum hash value, the probability that the minimum hash value will be the same between those two documents is 90%. Now, obviously, you don't want to rely on that because there's a 10% chance that it wouldn't be the same, and you'd say, in that case, if you just had a single hash code, you'd say, well, these things aren't the same at all because their minimum hash value isn't the same. Or if their hash value was the same, you'd say, well, they're 100% equal. If that's the only data you've got. So what you do is you generate multiple hash codes. And there's two ways to do it. One is to have multiple hash functions, and you take the minimum of each one. But the easy cheating way is you just take the minimum n hash values that you get. And that's what you kind of omit as part of your workflow. And then you do the join, and you count how many were actually the same in both documents. And if m were the same and you generated n, you just divide m by n, and that's your Jaccard coefficient. It's almost like magic. It's really weird. I've actually got an implementation of this in this open source project called Cascading Utils. We do most of our Hadoop workflows using this open source project called Cascading. It's kind of funny because Oscar was talking about Summingbird, and he mentioned Summingbird is built on top of Scalding, and Scalding is actually a Scala-based implementation on top of Cascading, and Cascading is an API on top of Hadoop, because you can never have too many layers in your open source cake. So in our case, we go to Cascading, which is a layer, sort of an abstraction layer above Hadoop to build these workflows. And so there's an implementation of SimHash in this Cascading.utils project. But it's pretty cool. You get your document, you turn it into a bunch of words, you calculate hash values for all those words, you take the minimum, pick a number, 100, right, hash values for each document, you omit those and you do a join, and you say, well, how many from document 1 were the same as in document 2, and that number divided by whatever it is, 100, is your similarity score. And that obviously scales. However, it assumes that the number of words you've got in your document is way bigger than the number of hash values you're generating. Like I mentioned, 100. I'm going to generate the minimum 100 hash values. That means I better have like 1,000 words in my document, something significantly bigger. So what happens if you're doing record deduping? With record deduping, you don't have like sometimes 1,000 values in a record, right? You got a couple words in a place name and a couple words in a street address. What do you do? Well, one of the things you do is you actually do this thing called set similarity join, where you have 3 passes. The first pass is you do statistics on terms, and you come up with a rank. Like, this is the most common word that occurs across our entire data set. And here's the second most common. Here's the third most common. You take that list, and you use it in the second phase where for each record, you just generate the terms that are by rank order. Like, you generate 10 terms, which are the 10 most common terms across your entire data set. And then you group by those terms or tokens, and you do the comparisons inside that group. So really what you're doing here is it's kind of like that zip code magic field thing I was talking about for doing points of interest. It gives you a way to have smaller groups of things that you're comparing. The basic approach to this has a bunch of issues, because typically, if you've got a record and you're generating these terms for it, you're passing around, you're creating a term and the entire record, and the next term and an entire record, and the next term and an entire record. So you have this huge data expansion problem. And there's approaches to get around that. One of the issues is if you have a term that occurs in every record, then that group is going to be huge. Right? Like if the term is, I don't know, street, and I've got all these records that have addresses, and street is in almost every one, then I wind up with this enormous group that creates an n-squared problem for the number of comparisons that I need to do. And you get an issue with multiple records being compared multiple times. But there's an open source project that talks about solutions to these problems. So this is if you're doing record level deduping, where you don't have lots of terms, right? Then you can do this set similarity thing. All right, so to summarize, similarity has a lot of value in a lot of problems or applications for things like recommendation. We talked about entity resolution. There's also deduping, right? There's clustering. All these things have similarity at the heart of them. And combining Hadoop processing with some kind of search index is a way to get like sort of all 3 things that you want. And in particular, it's the flexibility, because search gives you a really flexible way to adjust scoring. And so that's gives you a lot more dials to twiddle, knobs to play with, than you can with like regular recommendation engines. So if you have any questions, contact me at Scale Unlimited. There's a contact form. Pat Farrell's got this Hadoop plus Solr recommender project I was talking about, which is the thing of generating that co-occurrence matrix and then putting it into Solr. Mahout is the row, row similarity job. And then the fuzzy join project is the one I was just talking about here with parallel set similarity. So it's a university project. All right. We've got 3 minutes for questions. Who has questions? Anyone? Yes, you, sir.
Had any experience with this with kind of non-text or non-term friendly data, binary feature vectors, audio, video, image?
Right. So the question is, have I had experience with stuff that's not text? Right. Essentially doing similarity. So we have done some stuff with binary data, and essentially, as long as you can chunk it, then you can do things like creating a feature vector where it's like, what's the probability of each unique value? We haven't dealt with things like image similarity, that kind of thing. There's a whole other area of that we don't deal with. Yes, you, sir. Oh, how do you check if 2 addresses are similar? So that's an example of like inside of early warning. They got their own secret sauce, really, that does the comparison that says things like, well, how many, essentially, most techniques are similar. It's how many edits do I need to do to convert this address into that address, right? Do I need to fix 1 digit in the street number? Do I need to fix 1 typo in the street name, right? It's an edit distance calculation, typically. Okay. Any other questions? Yes? In the example I gave, SimHash, yes. Yes. So how accurate is this estimate, essentially, of the Jaccard coefficient using SimHash? Oh. Right. Right. So how different is it? So I did some tests where I generated like documents that had 1,000 words in it, where 90% were the same, and then I varied the hash size, the number of hashes that I generated. And if I only generated 10 hashes, then often like it would come up with numbers like 0.7 is the similarity or 0.95. It would vary quite a bit around it. When I got up to 100, it was very accurate. So basically 10% of a hash size, number of hashes equal to 10% of the number of unique terms. So my guess is somewhere between 5 and 10%. It would be a kind of a sweet spot. So you always just generate. So the question is, does it matter like the size of the document? And it actually doesn't. You basically generate a hash for every term in the document, and then you take the smallest n, whatever your n is, and that's what you're using for comparison. I know, it's kind of weird. It's like magic. Any other questions? Yes? So would it work to find similarities between medical transcripts? So yes, the key thing is figuring out what are the most important features. Like, I don't know, is it the one of the things you want to do when you've got like transcription data is you throw away the words that are too common. Like that's a really typical thing you do. So what you do is you first analyze your data and you figure out the magic number is 20%. If a word occurs in more than 20% of the documents, it's like a stop word. It's like and, of, the, but it's often very domain specific. So you throw away those words, and the ones that are left are the ones you use as your feature, and that improves the quality of your similarity calculations. So I tried the simplest thing that might work, which is that first, and then you can get into more creative stunts. Yes. We're using, probably standard analyzer is the common one. So people have done things where essentially you're creating character sequences, which are like 3 grams, 3 in a row, 4 in a row type sequences, and you can do that. My experience is, in general, we get better results with words as long as you remove the too common words, the words that are too common. So as long as you do stop word removal, we've seen better results with the term approach, but that might be very domain specific, right? It might be case by case.
One thing I really hate about stop words is they don't feel very principled to me, albeit I'm not a natural language researcher. I'm just wondering, and some of your documents are effectively stock documents. What if you build that log likelihood table and just remove, do you find, like the example you talked about, this entry page that everyone's going to be in on, are there pages that have no like kind of high information between?
Right. Okay. So, right. So the two things Oscar's bringing up, stop words by definition, it's kind of weird because you're just drawing a line in the sand and you're saying anything to this side we throw away and everything to that side we keep, and it's a step function, which you always hate when you're doing this kind of stuff. And the second thing that he brought up was, like what if you had a page that wasn't really related to anything in that item matrix? So the technique I use is I say, if I want to, on average, wind up with, let's say, 10 pages for each of the page here, and I know I've got 1,000 unique pages, then I'm going to want to come up with, like, let's say at max it'd be 10,000. So what I do is then I say, give me the top 5,000 entries from this co-occurrence matrix. I take some percentage of it, like half of them, and so then what I'll wind up with is sometimes pages which have no co-occurrences because their scores were too low. They didn't have any score that was in the top 50%. So it's a way of dealing with that problem of not wanting to have low scoring values essentially showing up in the index. So, all right, I'm in the red zone. Yes, I got to go. Anyway, thank you very much.